Hello again, welcome back to part 2 of our video lecture on calculus on parametrics. My P got a little destroyed here. Calculus on parametrics. That's what we're doing today. This is part 2. You should watch part 1 first, otherwise this is going to get pretty wild. It's going to get a little wild anyway. I have here a new set of parametric equations. I wanted to keep these guys polynomial for now. This is going to get a little messy. Try to keep it relatively okay-ish. We'll see what happens. As usual, first I want dy dx. And for that, I need to know dy. dy looks like it should be 14t plus 5 dt. Do not forget your dt. If you forget your dt, this whole thing is going to get real messed up. I also need a dx. My dx should be 6t minus 8 dt. Sorry, bud. So, for the first part of our problem, our dy dx, I just need to take these two things and divide them. So, dy dx is going to look like 14t plus 5 over 6t minus 8. At this step, the dt's will cancel, so I will leave them off. And we'll just have this. This is my first derivative. For the second derivative, I want to start with the first derivative. Dy dx equals 14t plus 5 over 6t minus 8. This is the first derivative. And to get a second derivative, I will take the derivative of both sides of this equation. So, on the left, that's going to give me d squared y dx. And again, ultimately, by the end of this, I want it to turn into a d squared y dx squared. I got to get that second dx in there somehow. That's what most of this work's going to look like. But for now, when you start with this and just take the d of it, you'll just have d squared y over dx. And when you take the derivative of this side of the equation, this is where the quotient rule is going to get involved. So buckle yourselves in. Here we go. Quotient rule says that I need the derivative of the top, which is 14, times the bottom, which is 6t minus 8, minus the derivative of the bottom, which is 6, times the top, which is 14t plus 5, all over the bottom squared, 6t minus 8, and I'm going to attach a dt to the end of the, 6t minus 8 squared, sorry. I'm going to attach a dt to the end of the whole thing. I ran out of room on my whiteboard, forgive me. Pretend the dt is attached at the end of this. So, I need to get a dx on the bottom here. I don't have a dx there. All I've got to work with right now is a dt. So, I'm going to come back to here. I'm going to use this relationship to substitute my dt for some dx's, after I do a little simplification, of course. I'm really cramped on space right now. You'll have to cut me some slack on this one. When I said it was going to get messy, I didn't mean physically. I've already got this derivative here. You remember what it is. rewind the video if you forgot. Put it in your notes. You'll be all set. Right now I want to worry about simplifying this. I need to take this bit, the 6t minus 8, and I need to divide both sides of the equation by that so that I get dx over 6t minus 8 equals dt. I need to get dt by itself. Once I have solved this for dt, I can plug it in here so that I end up with a dx piece somewhere in this, and I can divide both sides of the equation by that dx piece so that I get two of them on the bottom like I'm supposed to have. So first let's talk about simplifying this thing. I'm going to come over here a little bit. D squared y dx equals 14 times 6 is probably 84. 84t minus 14 times 8 is probably 112. Minus 6 times 14t is still 84t. And negative 6 times 5 should give me a negative 30. So this is what the top of my equation simplifies into. And that's probably going to simplify more even, like this 84t minus 84t, that's convenient. The denominator is still 6t minus 8 quantity squared. And now I'm going to swap out this dt that was attached at the end where it didn't fit. I'm going to swap that out for this. dt is the same as dx over 6t minus 8. That's my dt. And now that it's in terms of dx, I can divide both sides of the equation by dx to cancel that out. And again, on this side, dividing by dx gives me the second dx that I need to have on the bottom. So that's going to work perfectly to become this. And over here, I have a little bit more simplification I can do. The 84t's have canceled. I have a negative 112 and a negative 30. Those will probably combine to become a negative 142. On the bottom, that's all that's left on the top. The t's canceled, these guys combined, the dx is gone. This is it for the top. It's just a number now. The denominator here is going to be 6t minus 8 squared times 6t minus 8. So I'm going to get a 6t minus 8 cubed. There's 3 of them now. 2 from here, 1 from here. The dx's are gone, the t's are gone, everything else is accounted for. This is my final answer. This is the concavity of this function. So if you were curious to know whether this thing was concave up or concave down at a number like t equals 2, you can find that. You can plug t equals 2 into this thing right here, simplify it, do some math, it'll tell you the concavity. You'll probably get 12 minus 8 is 4. 4 cubed is 64. Negative 142 over 64 is a little less than negative 2. So when t equals 2, this function is concave down. It's already useful. Look at that. The derivative, the green stuff here, before I put the black d's extra in there, the derivative can be used to find slopes. If you want to know what the slope is when t equals 2, you can plug that in. 14 times 2 is 28 plus 5 would be 33 on top, 4 on bottom. So the slope at t equals 2 is about 8. The concavity is a little less than negative 2. And that's what you can use these things for. You could use the derivative and the second derivative to find where this function has maxima and minima, and where this function has slopes that are undefined, or slopes that are indeterminate. That's where it's going to get real bizarre. We're going to talk about that more in the third video. But looking just at this right now, looks like if you try to set the top of this derivative equal to 0, 14t plus 5, looks like t should be negative 5/14. So when t is about negative 1/3-ish, this function has a slope of 0. If t is negative or positive, t is positive 4/3, that'll make this denominator equal 0. At t equals positive 4/3, this function will have an undefined slope. The slope will be vertical, straight up and down. So probably, it's like the very first parametric equation we ever drew was a sideways parabola. This probably has some sideways parabolic aspects to it on some level. So that vertical slope where it's straight up and down, that's probably where it turns sort of sideways. So lots of valuable information to be had from these derivatives, these second derivatives. They're kind of a pain. This weird trick where you take a second derivative and it doesn't look right, and you have to do weird nonsense with the dt to turn it into a dx to get the second dx on the bottom. It takes some getting used to. It's not easy, but it's also not super difficult. It's just a little weird. You can do the thing. I'm going to cut this video here. The third video, probably going to be my last one. Third video is where this is going to get extra flippin' weird.